There are many different types of chemical reactions, and they are all equally important. By simply knowing what type of chemical reaction it is, allows you to predict what materials or compounds that reaction will generate. Combustion reaction is one type of reaction that's often used in the automotive industry. Gasoline contains this compound called octane, which is the active ingredient in the chemical reaction. When gasoline is injected into the engine, octane gets combusted or burned in the presence of oxygen. As a result, this produces carbon dioxide gas and water. This reaction generates a lot of heat and pressure, and it is this pressure that actually moves the pistons within the cylinders inside the engine. Down here shows you a balanced chemical reaction equation for the combustion of octane, which has the chemical formula C8H18. This reaction tells us that every 2 molecules of octane burned will generate 16 molecules of carbon dioxide. Other types of reactions are seen in batteries, such as the lead-acid battery used in automobiles. This is the same reaction happening when a metal is dissolved in an acid. This is what they call oxidation reduction reaction, or redox for short. All chemical reactions involve a chemical change, and a chemical change is basically associated with a change in chemical composition. In the previous lesson, you've learned the different evidences of a chemical change like gas bubbles, permanent color change, energy change, and formation of a solid precipitate. All of these terminologies here are basically synonymous with each other. They all mean the same thing because it results in the rearrangement of atoms to form an entirely new compound. Here's an example. A hydrogen gas reacts with oxygen gas to form water. This is basically a combustion reaction. Hydrogen gas is burnt to form water. Both hydrogen gas and oxygen gas are diatomic molecules, meaning they are molecules containing 2 atoms. This reaction produces water, which is 2 parts hydrogen and 1 part oxygen. Here you can clearly see that bonds were broken and new bonds were formed. The hydrogen to hydrogen bond as well as the oxygen-oxygen bond were broken, and oxygen to hydrogen bonds were formed. In other words, the atoms were rearranged. Now let's look at this same reaction here. Hydrogen gas is H2 and oxygen gas is O2. This right here is what they call a chemical reaction equation, and it tells us a lot of information. Both H2 and O2 are called the reactants. These are the starting materials, the materials you started out with before the chemical reaction took place. Any compounds on the right-hand side of the arrow are called the products. And these are the materials or compounds that you've made or synthesized. Shown here is the chemical formula of water, H2O. This tells you that in each molecule of water, there are 2 hydrogen atoms and 1 oxygen atom. The subscript letter G here in parentheses tells you the state of matter. The letter G indicates that it is water in gas state, or simply water vapor. It's important to indicate the state of matter in every chemical reaction because most compounds can exist in all 3 different states of matter. Another symbol here is AQ. This indicates that the compound was dissolved in water and not in solid form. Here in this reaction, you can see that there are two molecules of H2, one molecule of O2, and two molecules of H2O. These numbers in front of the chemical formulas are called coefficients. A coefficient shows the ratio between substances, acts as a multiplier, and is used in balancing chemical reaction equations. Here are some other symbols used. Plus means adding or reacting. Arrow means produces or yields. The next one means magnesium is used as a catalyst. H nu right above the arrow means light is being used as a catalyst. And finally, the triangle above the arrow indicates that heat was used as a catalyst. Any compounds on the left-hand side of the arrow are called the reactants, and the ones to the right are called the products. In every chemical reaction equation, such as this, it's very important that the number of atoms for each element in the reactants must equal the number of atoms for each element in the products. In other words, the equation has to be balanced. Is this chemical reaction equation balanced? Let's check by counting the number of atoms for each element on both sides, the reactant and the product. In the combustion of hydrogen gas, there's only two types of elements, hydrogen and oxygen, which is the same on the product side. On the reactant side, there are 4 hydrogen atoms because there's a coefficient of 2. And this basically acts as a multiplier. And we also have 2 oxygens. On the product side, we have 4 hydrogens and 2 oxygens. Here you can see that it is indeed a balanced chemical reaction equation. So how do we balance a chemical reaction equation? There are a few rules to follow. When balancing chemical reaction equations, add or modify coefficients in front of a chemical formula. You can't change the subscripts nor the chemical formula itself. Here's an example of a chemical reaction equation. We have the combustion reaction of methane, which basically produces carbon dioxide and water. The first step is to count the number of atoms for each element on both sides. Here we have 3 different elements, carbon, hydrogen, and oxygen. On the left, we have 1 carbon, 4 hydrogens, and 2 oxygens. And on the right-hand side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Here you can clearly see that the number of atoms for each element are not the same, not balanced, except for carbon. By simply adding a coefficient in front of the water, H2O, allows us to balance hydrogen. So here we added 2 in front of H2O. Now we're going to have to recount the total number of hydrogens and oxygens for the product side. So here we now have 4 hydrogens, because you can see that the coefficient 2 is a multiplier. So you're multiplying 2 by the subscript. So now we have a total of 4 hydrogens, and we do the same thing for oxygen. So again, 2 times 1, now we have a total of 4 oxygens. Here you can see that the number of hydrogens are now balanced on both sides. However, the number of oxygen atoms on both sides are not balanced. So by simply adding a coefficient of 2 in front of the oxygen gas on the reactant side, we'll make the number of oxygen atoms equal. Now the reaction equation is balanced. Here's another example. So the first thing you want to do here is to count the number of atoms for each element on both sides. On the left, we have cobalt, oxygen, and carbon. On the right-hand side, we also have cobalt, oxygen, and carbon. On the reactant side, we have 2 cobalts, 3 oxygens, and 1 carbon. And on the right-hand side, we have 1 cobalt, 2 oxygens, and 1 carbon. So here you can see that cobalt on the product side is 1 less than the number of cobalt on the reactant side. So what we can do here is balance the number of cobalt atoms. So by simply adding a coefficient of 2 here in front of cobalt would balance out the number of cobalt atoms. Next is oxygen. So you can see here that on the right hand side we have 2 oxygens, and on the left hand side we have 3 oxygens. So what we can do here is to find the least common factor in order to balance this. And the least common factor here is 6. So if we add a 3 here as a coefficient, that would generate a total of 6 oxygen atoms on the product side. So oxygen contains a total of 6 oxygen atoms, and because we added the coefficient here in front of carbon dioxide, the carbon is also affected. So we're going to have to recount the number of atoms for carbon. So on the product side, we have a total of 3 now. Now we can take care of the oxygen on the left-hand side, the reactant side. So we currently have 3 oxygens, but we need 3 more. So if we have a coefficient of 2 here in front of cobalt 3 oxide, that would generate a total of 6 oxygen atoms. Okay. So now, because we added the 2 in front of the cobalt 3 oxide, the number of cobalt oxide also changes. So now we have a total of 4 cobalt atoms. For carbon, you can see that we have 3 carbons on the right and only 1 carbon on the left. So what we can do here is we can add a coefficient of 3 in front of carbon on the reactant side. So now the total number of carbon atoms on both sides is balanced. For cobalt, all we have to do is change this coefficient right here into 4. And that would generate a total of 4 cobalt atoms. And all the atoms for each element is now balanced. So this is a balanced chemical reaction equation. Balancing chemical reactions involving polyatomic ions can be sometimes tricky. But one way to simplify this is to treat the polyatomic ion as one single unit, meaning you don't have to separate them into individual atoms, as long as that ion is present on both sides of the arrow. Here's an example. Again, the first step here is to count the number of atoms. Here you can see that the polyatomic ion phosphate is present on both sides, so we'll have to keep it as a single unit as shown here. So how many phosphate ions do we have on the reactant side and the product side? So on the left, for the PO4, we have 1 phosphate unit, 3 lithium atoms, 2 chlorines, and 1 strontium. On the right hand side, we have 2 phosphates, 1 lithium, 1 chlorine, and 3 strontiums. So when dealing with polyatomic ions, it's a lot easier to balance these polyatomic ions first. So you can see that the reactant side only has 1 polyatomic ion. And so by simply adding a coefficient here in front of the lithium phosphate would balance out the phosphates. So we need a coefficient of 2. Because we added a coefficient in front of the lithium phosphate, we have to recount the total number of lithiums. So here it's 3 times 2, a total of 6. So now you see that the lithiums are not balanced. So we have 6 versus 1. So by simply adding a coefficient of 6 here would balance out the lithiums. And because we added it in front of the lithium chloride, the number of chlorine atoms would also change. So now we have a total of 6. On the reactant side, we only have 2 chlorines. And so in order to get a total of 6 chlorines, we can add a coefficient of 3 in front of strontium chloride. So now we have a total of 6 chlorine atoms and also 3 strontium atoms. As you can see, all of the atoms, including the polyatomic ions, are now balanced. So this is a balanced chemical reaction equation. Balancing chemical reactions with fractional coefficients is sometimes necessary, but also tricky. Here's an example. As you can see here, the oxygen gas has a coefficient in fraction form after being balanced. So again, the first step here is to count the total number of atoms for each element in this chemical reaction. So on the reactant side, we have 3 different elements. We have carbon, hydrogen, and oxygen, which is the same on the product side. So on the reactant side, we have 2 carbons, 6 hydrogens, and 2 oxygens. On the product side, we have 1 carbon, 2 hydrogens, and 3 oxygens. So we can balance the number of carbon first. We can add a coefficient of 2 here in front of carbon dioxide, which gives us a total of 2 carbons on the product side. Now we will have to recount the total number of oxygen gas. So 2 times 2 is 4, plus 1, 5 oxygens. All right. To balance out the hydrogens, here you can see that you have 6 on the left-hand side versus 2 on the right-hand side. So to balance the hydrogen here on the right-hand side, we can add a coefficient of 3 here in front of H2O. That will give us a total of 6 hydrogens. And now again, we would have to recount the number of oxygen atoms on the product side. So now we have 3 plus 4 gives us 7 oxygen. All right, so now we have both carbons on both sides balanced, as well as hydrogens. So how do we because we have 7 here and only 2 here, we can use a fractional coefficient. 7 over 2 basically gives us a total of 7 oxygen atoms, because 7 over 2 times 2 gives us a total of 7 oxygens. So now the number of oxygen atoms is balanced. But the problem here is that we can't leave this coefficient as a fraction. One of the rules regarding coefficients is that they have to be whole numbers. So how do we get rid of this fraction? What we can do here is we can multiply the entire chemical reaction equation by the denominator of that fraction. In this case, 2. So now the chemical reaction equation becomes C2H6 plus 7 oxygen gas generates 4 carbon dioxide gas and 6 water molecules. So this is the balanced chemical reaction equation. Here's a few more examples for you to practice. You're more than welcome to pause this video if you'd like to try these out yourself. So for the first one here, we have the reaction between solid magnesium and oxygen gas. So again, the first thing that you want to do here is to count the total number of atoms for each element. So we have magnesium and oxygen. On the left-hand side, we have 1 magnesium and 2 oxygens. On the right-hand side, we have 1 of each. So if we add a coefficient of 2 in front of magnesium oxide, that will give us 2 magnesium atoms and 2 oxygen atoms. Now the number of oxygen atoms is balanced, and we can add a coefficient of 2 in front of magnesium to balance out the magnesium atoms. Next one here, we have hydrogen, chlorine, and cobalt. On the left-hand side, we have 1 hydrogen atom, 1 chlorine atom, and 1 cobalt atom. And on the right-hand side, we have 2 hydrogens, 2 chlorines, and 1 cobalt. So to balance this chemical reaction out, we can look at hydrogen first. You can see that we have 1 less hydrogen on the left-hand side. So what we can do is we can add a coefficient here in front of hydrochloric acid, HCl, and recount the total number of hydrogens and chlorines. So now we have 2 here and 2 chlorines. And now that's balanced. Last one here at the bottom, we have carbon, hydrogen, and oxygen on both sides. We have 4 carbons on the left, 8 hydrogens, and 2 oxygens on the left. On the right-hand side, we have 1 carbon, 2 hydrogens, and 3 oxygens. So how do we balance this out? Looking at carbon first, we can put a coefficient of 4 here in front of CO2. That gives us 4 carbons on the right, and recounting the total number of oxygens, that gives us 9. So the number of carbons is balanced. Now looking at the number of hydrogens, you can see that by adding a coefficient of 4 in front of H2O gives us a total of 8 hydrogens on the right hand side. So this changes to 8. Alright, but we would have to recount the total number of oxygen. So now we have 4 oxygens plus 8 gives us 12 oxygens. Alright, so the number of carbon atoms and hydrogen atoms are balanced. And so everything is balanced except for oxygen. So we can add a coefficient of 6 here. So we can get a total of 12 because we need a total of 12 on the reactant side to match with the 12 on the product side. Alright, so this is a balanced chemical reaction equation. Alright, and here's more balancing practice that involves polyatomic ions. So again, you can pause this video if you'd like to try these out yourself. So again, the first step here is to count the number of atoms and or polyatomic ions. So you can see on this one that the nitrite ion is present on both sides of the equation. Right, so we're going to keep it as a single unit. So we have 1 aluminum on the reactant side, 3 nitrite ions, and 1 calcium. On the product side, we have 1 aluminum, 2 nitrites ion, and 1 calcium. So the easiest way to do this is to balance out the number of the polyatomic ions first. So here you can see that we have 2 on the right and 3 on the left. So by adding, again, the least common factor here is 6. So we can add a coefficient of 3 in front of calcium nitrite and then a coefficient of 2 in front of aluminum nitrite. So now we have a total of 6 nitrites and 3 calciums. Alright, so now we can easily balance out the number of nitrites. We can add a 2 here, a coefficient of 2. And that would give us 2 aluminums and 6 nitrites. For the number of calcium, we can add a 3 here in front of calcium. That would give us a total of 3 calciums, and that would balance it out. Alright, for the aluminum, we just put a 2 here, a coefficient of 2. That gives us a total of 2 aluminum atoms. Alright, and that's a balanced chemical reaction. The one at the bottom here is another combustion reaction. So again, count the total number of atoms for each element on both sides of the arrow. So we have carbon, hydrogen, and oxygen. On the left-hand side, we have 4 carbons, 10 hydrogens, and 2 oxygens. And on the right, we have 1 carbon, 2 hydrogens, and 3 oxygens. So how do we balance this out? So again, we can look at carbon first if you like. We can put a coefficient of 4 in front of CO2. That would give us a total of 4 carbons. And then we would have to recount the total number of oxygens. 4 times 2 is 8, plus 1, 9. All right. For the hydrogens, You can see that we have 2 hydrogens on the right, 10 hydrogens on the left. We could add a coefficient of 5 here in front of H2O. Now we have a total of 10 hydrogens, and recount the number of oxygens. We have 5 plus 8, 13. All right, so both number of carbons and hydrogens are balanced, but not for oxygen. So this involves fractional coefficients again. And so what you can do is you can add a coefficient of 13 over 2 over here to balance out the number of oxygens, and then get rid of that fraction by multiplying the entire chemical reaction equation by 2. All right, and this will generate this chemical reaction equation that is balanced.